I'll work these problems two ways, one with the by hand method using the table, and then the second way with the faster way with the calculator. The first one, number 19, it says that the event is known to possess a normal distribution. That's the kicker. So now we know we're messing with stuff from the normal distribution section of this exam, and we can look there for formulas. The mean of this distribution is 460, and the standard deviation is 60. Between what times is the question? Did we expect most or 95% of the boys to run the mile? So this question gives us a probability and asks us to find the value. If we make the picture over here, the question is saying here's the distribution normal, so it looks symmetric like that. The mean, 460, is the middle, and then there should be two places around the mean so that we capture 95% of the boys, or 95% of the observations between these values. They're a negative x and a positive x. Because the curve is symmetric, we know they have the same value, or they're the same distance from the mean, so we just have to find those. Now, if we are doing it by hand method, we would first use the table to find the z-scores, and then second, turn that z-score into an x value from this distribution. And from reading the reference page, we can see the formula for x. So using the table to find the z distribution means we're looking for the z value for which this much area is to the left. And there's 95% in the middle, meaning 5% left over, and half of that 5% in each tail, or 2.5% there. So we'll look inside the z table in the area. I think I pulled it up here. To find inside here the area of 0.025. 0.021, 22, 22, 0.025. Aha, right there. So now we need this z value. Now that area, remember this normal table tells you area to the left of a z, so the one we just found from the inside of the table was 0.025. We want the z-score for that. It's negative 1.96, meaning that the z value we got from the table, negative 1.96. Then put this value in there to cook up the x value. Negative 1.96 times the standard deviation 60 plus the mean 460 is the x1 value, or this lower cutoff of the 95% of whatever the calculator says that is. Negative 1.96 times 60 plus 460 is 342.4 seconds. To find, that was x1, the lower bound. To find x2, the upper bound, we need to go back to the table to find the z value, and remembering that the z distribution, the normal distribution that is standard, has a mean of 0, so the positive value of that negative one we found would give us the upper cutoff. If you want to take the long route to that, you would say that the area now to the left of the z value we want is 0.025 plus the 0.95, or 0.95675. So we'd look inside the table for that value, 0.975, which we could do 0.92, 94, 95, 96, 975. There we go. Happen to be on the right column there. And that z value is 1.96 again, just like we expected. Very good. So that positive 1.96, we shove that into the formula. Again for the z value, so this new x2 value is the new value of z plus the mean. I suppose I should not overlap my stuff like that. Put this z value in there, and then see what the new x value is. So positive 1.96 times 60 plus 460 gives the upper bound. Whoa. I want to use this again, basically, but without that negative right there, so we can just arrow over and delete it and run the calculation again. 577.6. So the upper bound is 577.6. Now if we wanted to do this with the technology, let's see if I can find the using the built-in calculator functions, this would be an inverse normal problem. Inverse norm because we have the percentage and we're looking for a value from the distribution. The inverse norm always takes the area to the left, then the mean, and the standard deviation for this distribution. So we'd have to do it twice. First for the lower cutoff, inverse norm, the area to the left in this case first, 0.025, excuse me. Then mean, 460, standard deviation 60. And for x2, still inverse norm, but now more area to the left. That area to the left for the second one is 0.975. Mean still 460, standard deviation still 60. The inverse norm that we want is a distribution, so it's a second than the variables key to run the distributions. Number 3 for inverse norm. Area to the left in the first case is 0.025, mean is 460, standard deviation is 60, means that lower cutoff is 342, like we saw before. Then if we want to run the same thing again, second distribution, inverse norm, this area to the left is that red 0.025 from the picture plus another 0.95 from the black, like the area between. You can tell the calculator to do that addition for you within the distribution, which is kind of handy. And we find 577.59, or about 578 seconds if we were rounding what to the whole second, which matches the by hand answers. So now let's look at number 20. It says the amount of corn chips dispensed has been identified as a normal distribution, so we're still dealing with these humps. The mean is 16.5 and the standard deviation is 0.2. Suppose 100 of the bags are randomly selected and we want the probability that the sample mean exceeded the 16.6 ounces. Now this question is a little different because we are provided a sample size. So we know the underlying distribution is normal. We also knew from that distribution we chose 100 bags. We're trying to assign a probability to the mean. That's important. X bar is greater than 16.6 ounces. So the one thing we learned, this guy was from Chapter 8, Section 1, the distribution on sample means, and what it says is that when we assign probabilities to means, X bar, we have to adjust the standard deviation because the sampling distribution will have a smaller standard deviation. So we have to mess with a new sigma, we call it sigma X bar, the standard deviation of the sampling means. It's still 0.2, but now we can divide it, get smaller, by the square root of the sample size. 100. This formula is on the reference page. Sigma X bar is sigma divided by the square root of n. Now we can assign our probabilities under the new value for sigma. So let's just find out what that was like as a side point here. 0.02 divided by the square root of 100, which is 10. It's 0.002. So now we can work this problem just like we did number 18, but with an adjusted standard deviation because of the sample mean and this extra information we had about the sample size. So again, there were two ways. The by hand method, or the using the table method, means first find the z-score, which is x minus the mean, divided by the standard deviation, except in this case it's a sample mean, so x bar minus the mean divided by the standard deviation of the sample means. Like that. With the values we have from this problem, x bar is 16.6, the mean of the distribution 16.5, divided by either this thing simplified, we found it already to be 0.002, or if I plug in exactly the values for the square root, or exactly the values as they're written there in the symbolic notation, we could do that too. So now we have x bar 16.6 minus the mean 16.5 divided by 0.2 divided by the square root of 100. That's zero math in my head there, but at any point you could have substituted a predetermined value, like 0.6 minus 0.5 is 0.1, but this z value is 5. It's huge. So number 2, the probability that z is greater than 5 is where we check out the table. And probably be sorely disappointed, because if we're looking for the area to the right or the left, you'll notice that our z table only goes to 3.4. So for values of z more than 3.4, we'd use 1 to estimate the area. What we want to do, here's our curve. Here's 0, right? We're on the z distribution. 1, 2, 3 is about as big as this table gets. But we care about 4, 5 is the z value. So it's a very little area out there. In fact, so little area that the table says that that area past 5 is basically 0. Table actually says that the area left of 5 is essentially 1. So there's nothing left over to go to the right. Now if we want to check this out in the calculator, it'd be the same information that we did before in number 18. It's the normal CDF to assign probability. The minimum value, where we care about this, is 16.6. The maximum value is something sufficiently large, 10,000, 100, something big enough. The mean of the distribution, 16.5. And the standard deviation, which is adjusted because of the sample means, is now 0.002. Or you can let the calculator do the work again for you there. Find the distribution in the distribution menu, normal CDF, lower limit 16.6. The upper limit is huge. The mean of the distribution 16.5, and the standard deviation is 0.2 divided by the square root of 100 because of the sample mean. Paste that in. We find a probability of 2.8 e to the minus 7, which is fancy calculator language to say, let's do some big cha-cha slide here. 1, 2, 3, 4, 5, 6, 7 decimal places to the left, and each of those holes gets a 0. But like we saw from the table, basically no probability.